Thank you for coming to us today. My name is Michael Lennick,
And I'm Tony Lee.
and we've come here today to present and defend our design of the Firestorm processor that we designed for our CECS 440 computer architecture class. Just a quick overview of what we're going to be discussing today, where we came up with the name Firestorm, a brief history about the MIPS processor, and we're going to also be discussing our data types that we have, addressing modes, the instruction types that we have, as well as our enhancements and possible further enhancements that could have been done if we had more time. So the reasoning behind Firestorm is it's a comic book character that was an innovator for his time, and we felt like we wanted to innovate the market and expand in ways that haven't been expanded before. And because it also sounds pretty cool.
It is cool.
The original purpose for the MIPS, it was to make a microcontroller without interlocking pipeline stages. That's what MIPS stands for. However, it was later on adapted for teaching purposes into a smaller, more compact, modernized version that's called the Deluxe processor, and that is actually how we implement it in our class.
So our processor is, well, the MIPS. And as stated before, it is a microprocessor without the interlocking pipeline stages. So our processor is a RISC system, and it runs based off of a 32 load and store architecture, which just generally means that there is two parts to it, which is accessing memory and an ALU operation. So for our memory specifically, we're using a Harvard memory architecture, meaning we have separate instruction memory and separate data memory, which can be accessed at the same time. Our memories are based off of the big endian format, so the most significant bit is stored into memory first, and then the least significant bit is stored in last. Our processor has 32 registers. Each registers are 32-bit wide, and there's three registers that have specific functions, which is register 0, which always has a constant value of 0, register 29, which is the stack pointer, and register 31, which is our return address used for jump and link. The rest of the registers are general purposes in our processor. And finally, our flag registers consist of our carry flag, negative, overflow, 0 flag, and an interrupt enable flag.
Okay, now to addressing modes. For our processor, we have 6 addressing modes, being register, immediate, register indirect, PC relative, Pseudo Direct, and PC relative. So as you can see right here, we're representing our immediate addressing mode. The immediate addressing mode takes the immediate value that is stored in least significant 16 bits, and it uses, in the ALU, it is used as an operand. And then we also store the output of the ALU into the RT register. Now onto register addressing mode. Register addressing mode is when all the source operands and the destination operand is a register inside the register file. Now onto base addressing. Base addressing is when you have a register that has an offset specified by immediate value. That immediate value is sign extended. This is only used in our load word and our store word in our processor.
So next we have our PC relative, which is generally just having an operation that is related to the PC. What happens is that we have an immediate value, and that is added to or subtracted to the PC and used in our jumps, or no, our branches, I mean. Our next one is our register direct, which generally means the effective address is in our CPU registers. So in this case, our program counter is coming from the register, or the CPU register itself. And finally, we have our Pseudo Direct, which is kind of like a fake direct because it doesn't fill up the entire 32 bits. Here we have an example of the 26-bit offset, which is filling the register partially.
Next is our data types. In our processor, we only have two data types. We have assigned and unsigned. And unsigned, the values go all the way from 0 to all Fs. And then in signed, it goes at the medium point. That's where we see the two greatest values for both positive and negative being met.
Right.
We have 3 instruction types, or we actually have 4 instruction types. But these were a part of only the baseline, which is R-type, I-type, and J-type. So R-type means it's a pure register instruction, and it has to have an opcode of 00 with the function code specifying what we're actually going to be doing with the source registers. We have an RS and RT, which operate as our source registers, and RD, which operates as a destination register. We also have a shift amount, which is only used in terms of our shift right, shift left, and shift right arithmetic. I-type, we have a 16-bit immediate value stored tacked on at the end, with the opcode specified in the most significant 6 bits. And then depending on the opcode, we operate using the RS, which is the source, and then RT is our destination. Our J-type instructions is not for all of our jumps, it's only for the jump instruction, and it uses the 26-bit immediate value that's stored in the least significant bit, and it concatenates with the most significant 4 bits of the PC, the 26-bit immediate value, as well as tacking on 2 zeros. This allows us to jump to 1/16 of our whole entire instruction memory.
So here we have our connection for our 3 main modules, which is the CPU module, the I/O module, and the memory module. So for the I/O module, it is similar to the memory module, except there is one difference, which is how we implemented our interrupt. What we did was we added in an RS block, so then our interrupt is only activated once. There are 3 main buses, which is our control bus, which controls whether we want to write or read from either memory, and that control signal is coming from the CPU module. We have our data bus, which comes from our CPU module as well. It contains the D-out, which is the memory data that's being written into the memory modules. Our address bus, which comes from our ALU out, which addresses which address we want to write into. And then our 2 memory modules can interact back with our CPU module through the DMUX, where it outputs the memory data.
So the port is actually called DMUX? It's a 32-bit input called DMUX?
Yes, for our processor, that is, it's not called DMUX actually. I was just making sure that you knew that there was a MUX there, but it operates in front of the DY input.
So there's a DY input?
Yes.
Okay. And then the ALU out, you show it as bidirectional. Is that an input also?
Oh, no, I'm sorry, that was a mistake in the diagram.
And then what's the other bidirectional into and out from the
This one right here?
I/O module? No, you show a bidirectional.
Right here?
In other words, if you have arrowheads on both ends, it's
Yeah, that's the data bus. So you have data coming out from the I/O and going into the I/O. When you want to use an output instruction, you write to the.
So there's only one port to do both input and output? Or is that just, I'm a little confused. It shows only one port for input and output from that module. Is there one port or two?
No, we have 2 ports. We have an input and an output.
Okay. So this is a simplified diagram?
Yes.
Okay.
Yes. Next, we have the CPU module. This is used by instantiating a control unit, an instruction memory unit, and an IDP. It looks like we have 4. That's because I put the outputs coming from the CU all on the left-hand side and the inputs all on the right-hand side, so it's easier to see the flow.
Mm-hmm.
I only specified control words instead of putting all the symbols because you can't see all the symbols from sitting so far back.
Good.
We have, all the control signals are going into the instruction memory and the IDP. Then we have connecting between the instruction memory and the IDP is PC out, which is used to save the current PC when we have interrupt. We have the IR out and SciExtend 16. These are used to actually implement our instructions, and this is our certain key components that we need in the IEP. We have also the IR going to the control unit. This is used for us to be able to decode the instruction and figure out what control signals we need to feed into the IDP and the instruction memory unit. And also you can see down here, this is why I labeled it demux on the previous slide, because we have a mux that is taking in both the I/O and the memory data.
Mm-hmm.
So diving further into the schematic, there is our IDP module, which consists of the register file, the ALU, and the YMUX, and also little register files in between. So for the register file, what we have is a dual read port and a single write port. So any more than, or if we have any less than a dual read, then we'll require more clocks. But any more than a dual read, then we'll be wasting more money because there aren't many instructions that will utilize it. For our single write port, then we mainly only write to one register destination, or destination register, so that's why there's only one single write port. For what we also added in was a MUX right in front of the S address, so then it allows us to get the register from the instruction memory, and also it allows us to get the register 29, which is our stack pointer. We have a YMUX, which takes in the T address data, and also the sign extended 16 bits, immediate, and those are assigned to the RS and the RT, which goes into our ALU out. Our ALU out consists of 4 smaller modules. One is the general ALU, which has the regular instructions, regular instructions that are written into YLO. We then have our divide module, our multiply module, and our shifting module, which the shift amount comes into play, and it allows us to shift up to 31 bits. Below that, we have our other modules, which high and low are updated when the low signal is high, and our other registers are updated at every clock. We have our YMUX, which has a 3-bit signal that selects which data we want to output. Our output can be either written into a register, or it could be addressing an address in the memories.
And the D out as well is up here coming out from the RT, just making sure since my partner missed that sort of thing. So now diving into the instruction memory unit, we're made up of 4 essential parts. It's the PC MUX, we have a PC instruction memory unit, and the IR register. IR register holds in the current instruction register. This is not loaded at every single clock. It has a control signal that allows it to load at certain times. The instruction memory is only a read. We cannot write to it. That's why we have our instruction write strobe set to 0 at all times. And we have a chip select and a instruction read strobe so that we could actually read the contents of it. The PC out's coming from the PC register, which is also a loadable register. And then up here, our PC MUX has 4 inputs. We have an enhanced address type, a jump address type, a branch address, and a new PC, which could be used to load the PC with one of the previous PC that we stored. So now on to our enhancements.
So we had 6 new instruction enhancements, 4 of which are jumps. For jump if there is a carry flag is set, jump if negative flag is set, jump if 0 flag is set, jump if overflow flag is set, and then we have a wait for interrupt instruction and an unset interrupt enable. We did use the E-type that was given to us inside our
It was given to us as a requirement for our,
Enhancements.
Yes,
yeah,
for the
our E
enhancements.
key.
So what we did was we used the most significant 6 bits and assigned it to 1F, which allows the processor to know that it's an E-type. Then we used the lower 6 bits as the function code to determine which instruction it is. The middle 20 bits will depend, the usage of it is depending on the actual instruction itself.
So we did a jump of carry. This is the format. We are using the jump address, which is the middle 20 bits, and our function code is 00. This allows us to jump to 1/8 of our instruction memory space. This is beneficial for us because now we could jump further than our previous branches. As well as it allows you to jump based on if there's a carry from one of the shifts or from an unsigned arithmetic. Next is our jump if negative flag was set. This again is just ways of checking the validity of your numbers. This is beneficial because there is a way for you to be able to check the negative flag by using 2 instructions, but this could cost you 8 clock cycles,
Right.
whereas this only gives you 3 clock cycles. And as well, you could jump further.
So next is our jump if the 0 flag is set, and just like the previous other 2, it works the same way. It checks if the 0 flag is set, and if it is, then it will do a jump. So the benefit of this particular one is that it does it in 3 clocks, whereas a similar instruction such as the branch if equal can do it in 4 clock. So it makes it quicker, and also it allows the user to jump to a further instruction. So next we have the jump if overflow flag is set. So just like the previous 3, it works the same way. With the benefit of this, it lets us interact with our signed arithmetic, and it's not like the jump if carry where it will jump. Or what I'm trying to say is the jump if carry, the carry flag and the overflow flag works differently with the logic. So jump, if it was unsigned, then jump if carry will still jump, and jump if overflow will still jump. But since it is signed, then the logic is different. So then this one might jump while this one might not.
Can you go back to your explanation of 3 clocks on the jump if 0 versus 4 clocks on the branch if equal? Why would there ever be a difference? If one could be done in 3, why couldn't the other be done in 3?
Because this is only checking the current status register. So
What do you mean? It says if the present state 0 flag
yes.
has
Yes.
been set.
It's because for the branch if equal, then it has an extra instruction where you have to subtract to get the subtract the 2 registers to get the 0 flag.
Okay,
Yeah.
there you go. There you go. Thank you.
Okay. Then we also implemented a wait for interrupt. This allows you to put the processor in a lower power state because there's no switching of the electrical signals. And again, it saves you power, so when you don't need your processors to be constantly running, it will go into a low power state. And it allows the user to control the flow better of his code, as well as wait for IOs to update certain registers if there need be. As well, you have an unset interrupt enable. If you have a set interrupt enable, I just felt it was necessary that you need unset interrupt enable.
Yeah.
Just to make sure that like when you're in certain critical areas, you don't have another interrupt that occurs.
So those are enhancement, but due to lack of time, there are things that we would want to further enhance in the future, which includes a push and pop instruction, a no op, just so maybe the user wants to have the little wait, a rotate, a swap, so we can swap two registers, the value into two registers, a conditional return from interrupt, so then we can have more control on when we want to return, and a vector interrupt, so then we can have more than one different interrupts.
Yeah.
That is it. Is there any further questions that you guys have?
Excellent job.